Welcome back to Mr. Greenstein's Geometry. This is Chapter 11. We're in Section 11.5, Volume of Prisms and Cylinders. So the volume of a prism. The volume is really just imagine taking a little cube that's 1 by 1 by 1, and it's made of Play-Doh, and you try to put it inside of a prism. And each cube that you drop in there, you would count until you filled it all the way up to the top and you smooshed all those little Play-Doh cubes in, and that would be the volume. So it's the number of non-overlapping cubes that will fit inside a given interior. The volume of a prism is simply the area of the base. So the area of the base is down here, and the height of the prism. It doesn't matter whether it's a right prism, which means that the sides are all rectangles, or if the sides are parallelograms. It doesn't really matter. This volume is the same. So the volume of these two prisms are going to be exactly the same. There's Cavalieri's principle, which says that if two solids have the same height and the same cross-sectional area at every level, then they have the same volume. And if you look, if I took the cross-section of this right prism all the way down, I would have squares. The same thing with this oblique. If I was to cut it at any one point, I would have a cross-section that would look like a square. The volume of a cylinder also follows the same principle. So if I cut this cylinder, this right cylinder, I would get a circle, and the same thing would happen if I cut anywhere here in the oblique cylinder. Even though it's leaning over, the volume is still the same between the right and the oblique cylinder. And the volume calculated is just the area of the base, which happens to be a circle, times the height. And the height is always the perpendicular height. So let's calculate the volume of each one of these solids. So over here we have a trapezoid, and with a trapezoid base, and there's two of them, and we have a height of 5 centimeters. So I'm going to have a little triangle here. And the triangle is going to be 3 centimeters in this direction. What's this distance here? Well, since this is an isosceles trapezoid, then we know that the base of this triangle here is the same as this here, and that this 6 centimeters here is going to be the center part here, so that leaves 8 centimeters left over. So there's 4 centimeters here and 4 centimeters here. Therefore, I have a base of 4 and a height of 3, a base of 4 and a height of 3. So when I calculate this out, I'm going to have two triangles, and I multiply that 1/2 times the height, which is 3, times the base, which is 4. There's 2 of those. And then I'm going to add a rectangle. So this is the rectangle in the center here, and it has a side length of 6 and a height of 3. So side length of 6 and a height of 3. And when I add all of that together, I get 30 centimeters. So that's the area, or centimeters squared. That's the area of this base here. Using the formula for volume, I'm just going to say that volume equals the base times the height. So the area of the base is 30, and the height is 5. So then the result is 150 centimeters cubed. If I go over to the cylinder here, the cylinder is just the area of this circle. So the area of the circle I'm going to write as the base. The base equals 4 squared times pi. So that equals 16 pi. And then I take the height, which is 7 centimeters, and just multiply that times the base. So then the volume is going to be 16 pi times 7, and that is going to equal 112 pi, and that's going to be centimeters cubed. So that's how we calculate the volume of each one of those solids, and we're going to continue this discussion in our next section, part 2 of this section.